Welcome to our progress update presentation from Group 3. Small introduction, my name is Marijn Ruiter, I'm the communication manager of the team. I will now give a project description of this project. The assignment was given by the EPE, which is the Electromechanics and Power Electronics group. We were given a 1 to 5 scale model of an Audi A5 to conduct the experiments on and to use the programming on the car. We've done several experiments to make the tank-to-wheel analysis, the rolling resistance test, which will be done in the form of a goes-down test, the aerodynamic resistance test, which will be done in the form in a wind tunnel, and the dynamometer test, which will be done on a dyno. And with all these tests, we will try to find each resistance and try to make a tank-to-wheel analysis. And with this tank-to-wheel analysis, we can find the optimal driving speed of the car. And we also have a programming part, which consists of the LED system and the toll payment system. And the LED system is a system in which certain LEDs will give a color on the car, which in that way the driver can see at which speed he is driving. So the driver will be able to see whether he's driving at the optimal driving speed. And there's also a toll payment system. And the toll payment system is a system which there's a toll payment system on the track, and at this toll we will have to stop, and the car will receive the signal and output the signal to the toll with the number of the car, so the toll will know that the car has passed. The project goal is to develop and demonstrate a driving strategy for minimal energy consumption. We will find the energy consumption with the use of tank-to-wheel analysis and the conducted experiments. And with this tank-to-wheel analysis, we will be able to have a certain strategy for efficient city driving. So this also includes taking turns and finding the optimal way to taking these turns, and a stop at the toll payment system, which is also part of city driving. And we will demonstrate this solution during the Energy Challenge Day. And we might also have some improvements to the EPE team, since we are consultants. Our work approach, we've divided the tasks in sub-teams, because we feel that in that way we can work most efficiently. There is a programming team consisting of 3 people, which you can also see in the figure. And these people are responsible for making the LED systems work and the toll payment system work. We also have a rolling resistance team, which is responsible for finding rolling resistance forces and at different speeds, and finding the most optimal way at certain conditions at which the rolling resistance is minimal. And the aerodynamic resistance team, which is responsible for finding the aerodynamic resistance and making adjustments to the car so that the car will have a lowest possible aerodynamic resistance. And then lastly, the dynamometer team, which is responsible for the power output of the car and the losses at each part of the car, and helping with the tank-to-wheel analysis. And we also have a formal meeting every week in which we will tell what we have done so far and in that week, and whether you have any questions, and everyone will explain to the other teammates what they've done on their part and what they will do in that week, so that everyone is up to par and everyone knows how things are going on the other sub-teams as well. So the summary of this presentation, there will be an update by the programming team. There will be an explanation by the different subgroups leading the experiments. So each sub-team will tell something about their experiment, and we will end with a conclusion. So now I will tell about the rolling resistance test. The research goals of the rolling resistance are to get better insight into the effect of the rolling resistance on the energy consumption under different conditions, and we will calculate the rolling resistance with this formula. We will determine the rolling resistance coefficient on the RC car with different body setups and retrieve and analyze data from experiments done at the Meta Forum. We will determine the optimal car setup and driving speed with the analyzed data from the rolling resistance test together with the other tests. Our approach, we will use a common test, which is the goes down test. And in this test, the RC car will be brought up to a certain low speed, and then it will coast down to a full stop. So the only forces acting on the model car are the resisting forces. The retrieved data will be measured and measured by the Arduino and an SD card in the Arduino. And with the use of the SD card, we will be able to use these results and data in a laptop and make a graph and use this data. We will do the experiment in different conditions, so without the rear spoiler and front bumper attached, with the rear spoiler only attached, and with only the front bumper attached, and with the rear and front bumper attached. And we will see whether these conditions have any effect on the rolling resistance. And these conditions will be tested with two different setups, one with the cogwheel attached, so with the resistance of the electrical motor taken into account, and one without the motor cogwheel attached. After the experiments, we will use these formulas to find the rolling resistance. So because the car is coasting down, the only forces acting upon it are the resistance forces, and because with the SD card measuring the speed and the time, we will find the acceleration, and the mass of the car is known, so we will find the resistance forces. And the resistance forces consist of the aerodynamic force and the rolling resistance force. And the aerodynamic force is known from another experiment, so we will now know the rolling resistance force and can find the missing variables. So now Bruno will tell you something about the programming part.
Hello everybody, I'm Bruno. I'm part of the programming team of a project. So the goals of the programming team are to create a speed measurement system. This is done with a RPM sensor that is mounted on the car. That RPM sensor will transmit a signal to the Arduino board, and the Arduino board should send a signal back to the LEDs that are mounted all around the car to light them up. So the output of the LEDs should be the optimal speed. We should see the optimal speed on the LEDs and design a proper pattern to make it easy to understand if whether we are going to the right speed or not. Well, the optimal speed will be calculated in the further weeks, thanks to the results of all the experiments. The next goal of the programming team is to create a toll payment system. So on the challenge day, every round you do around the track has to be counted, and we have to do that thanks to a toll payment system. So the car should receive an IR signal from the track buildings, and then the car should send a radio signal back to the computers of the organization, and that should be the base of our toll payment system. So what we have done so far is to create the RPM, to calibrate the RPM sensor so we can measure the speed at which we are going. So we receive the signal from the RPM sensor, and we can, by different manipulation, calculate the speed at which we are going. And then, with that speed, we can create a program that lights certain LEDs on in different colors, and that's it. So the toll payment system, we have done it at this moment. We soldered the PCB that is actually here. You can see the IR receiver. And the IR signal is properly received by Arduino, and we programmed properly the radio signal that should be transmitted back to the central computer of the track. So we encountered some issues during the programming tasks. At first, it was not clear if which pin did control the radio on Arduino, but thankfully it was an error in the documentation we received, so we managed to fix it. And it was also challenging to light up the full bar of LEDs in a certain color, but after a few calculations, we managed to do it. So now our plan to improve the project is to verify the accuracy of our speed system. We are sure it measures a speed, but we want to see if it is properly calibrated. So we have to undergo some tests. And then we need to design a clear pattern to indicate whether we are going at the right speed or not. Because now it's simply the full bar is in a color if we are going at a certain speed, and we would like to do it more progressive. We would also like to improve the efficiency of the program, because we think that the accuracy of the speedometer is not very perfect due to the length of our program. So we need to work on the efficiency of the program. So now I will demonstrate you what the light bar looks like. Oh. Well, it's not a problem. Basically, the speed goes up quite. When the speed goes up, we have first a blue full LED bar when it's not at the right speed. Then when we come into an interval where we should state that the speed is quite optimal, the whole bar turns in green. And when we are going too fast, the whole bar is in red. And when we are coasting, there is a problem. Due to the inefficiency of our program, the colors change not fast enough. So that is what we would like to improve, but unfortunately I had a problem with the video. So now I will let speak my colleague Cosco. He will tell you about the aerodynamic drag force. Thank you.
Thank you, Bruno. I'm going to present the aerodynamic drag force. And at first, I would like to begin with the question, what exactly is aerodynamics? Aerodynamics is the way that objects move through air. It is a force that most people neglect. It is a force, a fluid, that we move through on an everyday basis, but we don't pay much attention to it owing to its low density. For example, the water is really hard to move through because it has a really higher density. Therefore, there are a lot of forces, and I would like to talk about the drag, which is pictured here in this figure, and lift. The force lift is a force that's moving the object up, and the drag force is slowing the object down. So, therefore, we would like to make these forces as low as possible, to have as much efficiency as possible. So, to sum this up, aerodynamics, the characteristic of the car, is leading to energy loss, which is the main issue that we're trying to prevent in this course. We're trying to move through a route as energy efficient as possible. Therefore, we should lower these forces. As stated here, we have the air drag formula, and each of these values should be as low as possible in order to achieve the minimum value for the force. P here stands for the air density, C is the air drag coefficient, A is the car frontal area, and V is the velocity. As you can see, the force depends on velocity quite a lot, which is squared. Therefore, increasing the velocity 2 times is going to lead to a 4 times higher force in order to prevent the aerodynamics drag, which is slowing the car down. Therefore, modifications of the upcoming experiment, which are stated here, is the first one of them is going to be to add a rear spoiler, which is going to possibly increase the drag coefficient, but also it is going to decrease the flow separation which is happening at the rear part of the car. I think a rear spoiler is going to decrease the flow separation, but as well increase the drag coefficient, and we're going to find out at exactly what value is going to is going to give us. And as a second, we're going to add a bumper, which is going to be placed in the front part of the car. The front part of the car is the part where the car experiences most of the aerodynamic force, as you can see here. Therefore, we would like to lower it as much as possible. The bumper helps the aerodynamics characteristic of the car by not allowing the airflow under the car. That's why, owing to this, the air drag coefficient might go lower, and we're going to create a downforce, which is going to increase the grip of the car and to have higher stability going through corners. As a third experiment, we're going to add them both, depending on the results that we achieve from adding the rear spoiler and the bumper. If they're both beneficial to the efficiency of the car, we're going to try this experiment. If not, then it would prove to be pointless. I have added an optional additions, which are going to be the addition of duct tape. As we can see here, the flow separation is one of the main forces that are slowing the car down, except for the front drag. Therefore, we would like to decrease this as much as possible. So, we're going to add duct tape in order to make the body smoother as a teardrop, which is the most aerodynamic thing in existence. An important note that we should add is that we assume the battery is fully efficient, because it is going to... The experiment is going to be conducted in a wind tunnel. In this wind tunnel, the air circulates in an enclosed route through ducts, which are air ducts, which are displayed here. They are with different shapes and sizes. The motor fan compensates for the pressure loss, because when air moves in that direction, at the end part it loses its pressure. Therefore, the motor fan compensates for that, and a small opening that's created there is for preventing this. And owing to this fact, the pressure during the experiment is the same as the local air pressure. As you can see here, this is the platform in which the car will be placed. The reason for this platform is that the car is not going to have any rolling resistance at all. It's going to be a total zero, so that we can make the accurate values of the air drag coefficient and the air resistance force at total. We can see here that the platform is connected with a wire to the force sensor, which indicates the force that the air is exerting on the car. And using a variable resistor, the airspeed can be adjusted, which can be a maximum at 50.4 kilometers per hour, and also calculate the difference in air pressure. As you can, and after this experiment, after acquiring the results, after acquiring the air drag coefficient and the force at total, we can calculate at what speed we should drive during the final test to prove that our car, with its modifications that we have stated here, is going to be as efficient as possible. And driving at low speeds doesn't mean that it's going to be more energy efficient, because that way we're going to neglect the other rolling resistance forces and etc. Therefore, I would like to end with this my presentation. I'd like to give the word to Jay, who is going to speak about the diameter test.
Hi guys, so my name is Jay and I'm going to talk about the dynamometer test. So when we go further, so firstly I would like to talk about the introduction of the basic test. So dynamometer, what does this mean? So dynamometer is a device which calculates the speed and the torque of the engine at the same time with the help of a rotating prime mover. Now what does that mean? So basically what we're going to do in this test, that we're going to have a roller bench which is attached at the dynamometer, and we're going to have a car who's in different situations, whose wheels are going to be attached, those rear wheels are going to be attached to the roller bench, and we're going to check the power consumption in different cases. So the working says that, as I told about the introduction, that it tests every rotating portion of the drivetrain, as when we connect the car on the roller bench, from the differentials and the motor to the tires, everything is actually checked and rotated through this test. It confirms the torque, power and the torque provided by the engine. So that is our main motive of doing this test, is that to determine the right torque and the power that we can provide to our model car, and actually can simulate a real world application of the equipment. And I would also like to mention that the dynamometer test is one test that can actually help people to minimize, or to let people not take the road, the rest which happens on the road, because it requires less time. It's quite efficient. So moving further, I would like to talk about the objectives of our test. So we would be determining the power consumption and losses from tank to wheels, and the overall efficiency plot with speed and force for our model car. We will also have a look on the auxiliary losses, especially the ESC and its power supplies. Now the materials and equipments required, because it's going to be a little more of dynamic test, so we need a lot of things which are going to be included in a test. So firstly we will talk about the roller bench, because the car would be placed on a roller bench which will help it to rotate and determine the power losses. Then we'll have a main control cabinet, the current and differential probes. The current and differential probes are basically two devices used to measure current and voltage separately. And last, we have the software with the control GUI. So this software is basically used to determine the battery current, the battery power and the battery voltage simultaneously with the velocity of the dynamometer roller, the force exerted on the dynamometer roller, and the distance covered by the car. Now our experiment situation. So we have three different situations. In the first situation, we have the motor cog wheel removed. So we don't have the motor inside the car, and we test the car without the motor in this situation. Situation 2, the motor is connected to the battery, and situation 3, motor connected to battery but with zero speed. I mean the idle consumption of the car. I would also like to throw some light on the power balance equation for situation 1, which can be further cleared after I show you a picture of the situation with the Sankey diagram. But looking at the power balance equation, I would like to say that in situation 1, when there is no motor connected to the battery, the power comes from the dyno roller, goes to the wheels of the car and then goes up to the differentials and then goes out. So from this equation, what I'm trying to show is that the torque 2 and the omega 2, which is of the roller, which is used to calculate the power of the roller, the power comes from there, and PRR is actually power of the roller resistance, the power which is actually the loss, the power loss which is taken into account due to rolling resistance is subtracted from the initial power which is inputted from the dynamometer, and minus power of losses driveline. So there are a few losses which also occur in the driveline, so the power related to these losses are also not taken into effect. For the situation 2, we have two different equations for the power, because now the motor is actually connected to battery, so it's pretty obvious that there are going to be certain power which are going to be now included as compared to the first case. So power of battery, now power of battery comes into action. So there's going to be initial power which is going to be entering from the battery, which is the input power, and we could actually calculate that by by voltage into current. So power battery gives us the power for motor, and there are going to be a certain losses with the battery associated as well. Now when we talk about the power which is related to the motor, we will obviously have a little resistance from the first experiment that we did, because there's going to be a little power lost while we perform the first experiment, as in the first situation, and then of course the power which is given to the roller. In situation 1, when the motor cogwheel is actually removed, when there's no load measurement, we actually talk about the power. I think I've exceeded the time limit. So situation 1, the motor cogwheel, when it's actually removed, I would say that in this case the power comes from the dynamometer, goes through the wheel, and then it further goes to the differential. So the Sankey dynamics explains itself very clearly that the power is coming inside, and there are few losses from the dyno and the rolling resistance, and from there the power straight away goes to the losses, to the differential in gears, where it also has a few losses. So there is no further contact of the motor cogwheel in this situation. In the next situation, the motor is connected to the battery, and from the Sankey diagram, it would be really better for me to explain, because the battery input is actually this battery. The power comes from the battery, it goes to the motor controller. Obviously, there are certain losses which are taking place in the motor controller, and then it moves to the differential, to gauge in the differential, then it goes to the wheel, and then further it goes to the dyno. So the useful power which is actually going to the dyno is considered at a separate place, because there are going to be a lot of losses that are going to happening from the battery till the wheel. There are going to be ESC, which is actually a loss from the battery input power, and there are going to be motor losses from the motor, and gears and differential losses from the gears and differential. Now when we move to the situation 3, the motor is connected to battery but with 0 speed. So here what we're trying to determine is that our auxiliary losses are going where. How do we actually get to determine these losses? So everything is connected, but the car doesn't move, because we want to determine the auxiliary losses which are being consumed in the car. For example, the LED light beams and the auxiliaries such as the cables. And then the results from the dyno test. So here I would also like to throw some light on the speed load road profiles and the speed load road profiles, because we want to make these profiles in order to determine the right speed for the right speed with the right force, in order to actually determine the accurate efficiency of the car. Now when I move to the conclusion, I would just like to say that as we already talked about a lot of things, the programmers, the rolling resistance and the wind tunnel test, so we're basically working on all of these tests to actually determine the right efficiency and the right speed of the car. And I would like to say that till now it has been very good to work on all the aspects, and we're looking forward to have a wonderful project. Thank you.